So we're going to start out first with the definition of a linear equation. So we say a linear equation in the unknowns x1, x2, x3, all the way down to xn has the form, the summation from 1 to n, ai times xi, which just means a1 x1 plus a2 x2 plus etc. down to an xn is equal to b, where the ai's and the b are just regular old real numbers. When we talk about linear equations, oftentimes what we're interested in are solutions. So once we have a linear equation in n unknowns, a solution to that linear equation is an element s1, s2, down to sn that lives in Rn. So there are n real numbers, such that when you plug s1 in for x1 and s2 in for x2, etc., you get b. In general, the set of all of the solutions to an equation forms what we normally think of as the graph of the equation. So as a nice example, let's consider the linear equation in two unknowns, 2x plus 3y equals 5. There are lots and lots and lots of solutions to this, and they're just pairs of numbers, an x and a y. One possible, easy to see example is the point 1, 1. So when I take the number 1 and plug it in for x and plug it in for y, I get 2 plus 3 is 5. If I want all of the solutions and I want to understand geometrically what all of these solutions form, all I have to do is solve for one of the variables in terms of the other. In particular, it's customary to solve this equation for y in terms of x. We can represent this as a set of pairs. Being a set of pairs, this is naturally a subset of R2. So to graph the set of solutions, all we need to know is this is a line with slope negative 2/3 passing through the point 0, 5 and 15/2, 0. So the set of all solutions to a linear equation in two unknowns is simply a line in the plane. Now oftentimes, linear equations in and of their own selves are not particularly interesting. For linear algebra, we are more interested in what are called systems of equations. So a system of m linear equations in n unknowns is a collection of one equation, a11 x1 plus a12 x2 plus etc. down to a1n xn equals b1. Note here that the first subscript indicates which equation this goes with. The second subscript indicates which variable the coefficient goes with. A second linear equation in n unknowns, keep going. We have m equations, each one having n unknowns. So in particular, there are m rows and n columns. Usually, instead of saying a system of m linear equations in n unknowns, we will simply refer to this as an m by n linear system. We're going to talk about a lot of concepts in this class, but almost every single one, no matter how abstract, no matter how strange it seems, will almost inevitably boil down to solving one of these systems. So what we need to know is, what does it mean to find a solution? So for an m by n linear system, when we say a solution, usually what we mean is a simultaneous solution to each of the equations involved in the system. So when we take all of the solutions to the system and combine them into a set, we call that set the solution space to the system. Finally, we say two systems are equivalent if they have the same solution space. Now these may be two systems where the equations are not the same, or maybe they're not in the same order. There's something different, so the systems are not equal, but their set of solutions, those are the same sets. That's what we call equivalent systems. It's going to become a very important thing as we move through this. So if we want to check that a point, in this case 2, 3, is a solution to a system, that means we have to plug the number 2 in for all of the x's, plug the number 3 in for all of the y's, and make sure that both of our equations are satisfied. So when we plug 2 in and 3 in to the top equation, we get negative 2 plus 3 is 1. And when we plug 2 in for x in the bottom and 3 in for y, we get negative 4 plus 3 is negative 1. Great. Some motivation for why we might be interested in solving linear systems. Linear systems actually arise very naturally. One of the ways in which they do is in calculus. So let's say we wanted to compute the following integral. So in calculus, we're told that in order to integrate this function, what we should do is write down the following equation. We clear denominators, we expand, collect like terms, and we get an equation. In order to get these variables, a, b, c, and d, we say to ourselves, oh, I have a polynomial on the left and a polynomial on the right. For these two polynomials to be the same, they have to have the same coefficients. Okay, well, the coefficient of x cubed on the left is 0. The coefficient of x cubed on the right is a plus b plus c. Those have to be the same. Next, since the coefficient of x squared on the right is 6 and is negative a plus b plus d on the right, we get 6 equals negative a plus b plus d. Continuing in this way, we get a system of 4 equations in 4 unknowns. As long as we choose a solution to this system, then we can write down a, b, and c, and d over here, and we can integrate our function. So up next, we'll discuss how we can manipulate systems equations, and this will be our first step towards a method for solving all linear systems.